So the material that's going to be covered on the next exam is chapters 4, 5, and 6. And what I want to do first is share my Blackboard and just show you guys where it is. And well, for other reasons, but let me get in there first. And let's see if I can find it. I think it's here. And there it is. There's my Blackboard. Actually, that's my email. But I use
my picture of my meeting.
Yeah.
And then I popped it on, and there he was. I was like, well.
I use the web Outlook instead of my my Microsoft Office.
Oh, okay.
For Southern, I link my New River account into my Microsoft Office, but I don't do that for Southern so that I don't get them confused. But here's the. I'm gonna shut this phone off. Junk calls start at 9 o'clock. So I'm going to go into, let's see, over here, online class, right? So we'll start that up, and tell me if you don't see what I'm talking about, then let me know. And then I'm going to go to the course, which is 203 here. As long as you can still see it, we're fine. That's what you should see. And then you go down to learning modules.
Yeah.
Okay, and scroll down to exam 2.
Okay.
And there you'll see all the links to the recordings for the lectures here. And of course, I'll post the one from today probably within 24, 36 hours.
Okay.
And
I'm run him to the bathroom.
These all with the red on them, those are previous semester recordings. You don't have to bother with those unless you're just interested.
I opened one up and looked, and I was like, well.
Okay. Yeah, those were probably where I was standing in front of the class, in front of a board. Yeah. Okay, so you will be able to see the exam here, right? But you also see these 3 items here above it.
Right.
Helpful hints for chemical equations, polyatomic ions, and periodic table.
Right.
You can, it's legal for you to access those documents during the exam.
Right.
The problem I found is, though, once you get into Lockdown Browser, it won't let you open these items. So what you need to do is go in there first and print them off before you go into Lockdown Browser.
Oh, okay.
Okay, so that you'll have them there with you.
Okay.
You need the periodic table, definitely.
I've got that. I did my own. I hope I got a good grade on it. I worked really hard on that.
Polyatomic ions.
Points where I bombed that test.
Yeah. So be sure and get those before you go in to Lockdown Browser and start the exam. Then you'll have that information with you.
Right. Okay.
All right.
I'm gonna take him to the bathroom real quick.
Okay.
I'm sorry.
I'm just gonna keep talking.
Okay, you just go right ahead.
Yeah.
Thank you, sir.
All right. Okay, so now that we've covered that and where to find the exam, I'm going to stop this share, and I'm going to call up, let's see, I want to open another document here. Okay, you can't see this yet, I haven't shared it, but I want to, let's see, where's my Zoom? Here. There we go. So now I want to share I'm just going to share this periodic table, and it's going to sit there the whole time because we need it all the way through this discussion. I'm going to leave the periodic table up there. There we go. So I can make it bigger. And let's see, maybe I could make it another 10%. Yeah, that should be big enough. Okay, So the rest of the discussion I'm going to be putting on the board because I've got a document here that I use for review. Actually, this one comes from previous semester, but I don't have it in a form that I can share it. So I'm going to have to put these items up on the board, and I've got them marked off here, and I'm going to go through them one by one. And the first one has to do with how do you read the periodic table to determine charges on the elements when they form compounds. So say we have a group of elements where we want 1A and then maybe 7A. If you look at, that's the old system. So if we look at 7A here versus 1A over here, you'll notice that 7A is all halogens, and the halogens are all -1 charge whenever they form a compound with a metal, right? So you remember this one doesn't have the black line on it, but if you follow this, let's not, maybe I can annotate. Let me draw a line. So if you follow this line here, and then you go down there, then you go down there, that divides metals from nonmetals. Okay. So anything on the right-hand side is a nonmetal. And anything on the left-hand side is a metal. So if you get a nonmetal and metal together, their preferred bonding mechanism is ionic. So you need to know the charges on your metal and your nonmetal so that you know how they bond together. So if we pick the 1A versus the 7A, and the 1A over here, this would be, let's see, that would be alkali metals. They're all +1 charge. Always +1 charge. By the same token, the 2As are always 2+ charge. Those are alkaline earths. The 3 group over here, boron, well, not so much boron, depends on what it's bonding with, but aluminum, gallium, and indium, those 3 are all +3 charge. So if you're going to make a bond with a plus, you need a minus, and the minuses come from over here in the nonmetals. So the fluorine, chlorine, bromine, all of these guys over here, excuse me, under that one are -1 charge. So whenever you get a 1A or a alkali metal with a halogen, it's always +1 here, -1 there. So you only need one of each. For instance, lithium and fluorine. If we form a compound with those two, lithium is a +1 charge, fluorine is a -1 charge, and all you have to do is make sure that the charge is balanced. So +1, -1, you only need one each. That's it. You're done. If we did something like magnesium and chlorine, right? Magnesium comes from the second group. It's always a +2 charge. And chlorine is still a halogen, so it's a -1 charge. So that means you need 2 chlorines, and you're balanced. The nice thing about the periodic table with the old numbering system here, 1, 2, 3, 4, 5, 6, 7, is that those Roman numerals tell you how many valence electrons there are in the outermost shell. So you remember when we were doing electronic configurations for our elements, the number of valence electrons were the number of electrons that were in the highest numbered shell. For instance, if we draw oxygen, right? Oxygen has 8 protons. That means it has 8 electrons, as long as it's not an ion. Right? So we have 8 electrons, and if we draw the configuration, we have 1s2, a 2s2, and a 2p4. Right? So that means the highest number is 2. Add them up, you have 6 valence electrons. Okay, so what does that mean? Well, we combine the valence electron numbers with the concept of the octet. And in order to get an octet, oxygen would have to acquire 2 more electrons to make 8. That's what octet means. So that's why oxygen prefers, in its charged form, to be a 2- ion. So the ion of oxygen is typically 2-, whenever it is bonded with a metal. And you can do that with any of these. The halogens are 7A, which means they have 7 valence electrons, and they only need 1 electron to complete their octet. So that's why all the halogens are a -1 charge whenever they form their ions. The nitrogen group, the ones with nitrogen, for instance, phosphorus, they have 5. See it? 5 Roman numeral. They have 5 valence electrons, which means they need 3 more to make an octet. So those in the nitrogen group, like phosphorus, tend to form 3- charge. Okay. On the other side, for metals, say calcium. Calcium is in the second group, so it has 2 valence electrons. Right? So if calcium has 2 valence electrons, which is easier? Add 6 to make an octet, or just subtract 2? Well, they subtract 2. So that means calcium prefers 2+. Now, why do they subtract 2 and not add 6 to make an octet? Well, if we do the electronic configuration for calcium, we need to know how many electrons, which is 20. Okay. I better start this over again. So for 20, we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So count them up. 2, 4, plus 6 is 10, 12, 18, 2 is 20. So there's the electronic configuration for calcium. Now, in order to have an octet, the highest occupied shells in its structure have 8 electrons. So if we go out here to 4p, we would have to add 6. That's more difficult to do than if you say, all right, we're going to have an octet this way. We're going to get rid of those 2. Now the highest shell is 3, and we have an octet. So that's why you lose 2 electrons in metals, or lose electrons in metals. In case of calcium, you lose 2. And that gives you a 2+ charge. And remember, the charges are always based upon the balance of protons and electrons, which means you either add electrons or you lose electrons. If you add electrons, you get a minus charge. If you subtract electrons, you get a positive charge. Can't touch the protons. If you try to modify the protons, you have a different element. Okay. So that's one thing that you can glean, one useful bit of information you can glean from the periodic table. What family is it in? What group is it in? And then you can determine the charge when you try to write your compounds. Okay. Let's see. Let's take an example. If I say we want to form a compound between sodium and arsenic, okay, how would you approach that? Look at sodium, look at arsenic. Where are they coming from? Sodium is here. It's a metal. Arsenic is over here. It's a nonmetal. So we're going to have an ionic bond. That means transfer of electrons, complete charge. So sodium, being in the first group, is going to be a +1 charge. Arsenic is in the same group as nitrogen. And what charge is it? Well, you can do it a couple of different ways, but the simplest way is say, this group is -1. This group is -2. This group is -3. Go down here, arsenic is -3. So balance the charges now. You need 3 pluses to balance that 3 minus. That means 3 sodiums. So Na3As is the proper formula for the combination of sodium and arsenic. All right. Now, what kind of bonding, what other kind of bonding do we have available to us? Well, if you can't, if the strength of attraction, and we studied that in chapter 5, electronegativity. If the electronegativity difference between the two atoms is not strong enough so that one of them can take electrons and the other one give them up, then what you have is the probability that you're going to share electrons. And if you have a metal from way over here, excuse me, over here somewhere, and versus a nonmetal, you're typically going to have an ionic bond, which is the electronegativity of the metal is low enough so that it will give up electrons. And the electronegativity of the nonmetal is high enough that will accept them. And that will give you an ionic bond. But if you try to form bonds between two nonmetals, where their electronegativities are very close together, then they tend to share electrons rather than transfer them. So for instance, if you have, let's take something simple. Let's try, let's just take a binary compound that's made up of the same element, like oxygen. Right? Then it's obvious that neither one can extract electrons from the other. Right? They have the same electronegativity. So what do? Well, they share electrons, right? And the Lewis dot structure is a way to account for electrons in the valence shell, right? So for oxygen, the number of valence electrons is equal to that Roman numeral number right here. So oxygen has 6 valence electrons. So how do you put them around the oxygen? Well, you start going around and around and around and around. There's 4, there's 5, there's 6. And then we can go around like this. There's 6 around that one. So how does oxygen get an octet out of that configuration? Well, it's more of a mind game, you might say. Oxygen thinks it has access to 8 electrons if it shares these 2 with this oxygen's 2. So it forms a bond here, and it forms a bond there. Okay, so now this oxygen thinks it has 2, 4, 6, 8. And this oxygen says, I think I have 2, 4, 6, 8. That's the octet. And the bonding of oxygen in this case is a double bond, right? That's one, that's the other one, that's one, that's the other one. Each line represents 2 electrons. And then you have these others out here. Non-bonding electrons. Sometimes we call them lone pairs. And this is a covalent bond. In fact, it's non-polar because there's equal pull on both sides, 2 electrons. The electron density around this molecule is evenly distributed. It does not form an unbalance in the charge distribution. So that's definitely a non-polar covalent bonded molecule. If you have a difference in electronegativities, but you still have a covalent bond, for instance, with water, and you have a hydrogen out here and a hydrogen out here, each of those hydrogens only has 1 electron. Okay? Oxygen still has its 6 electrons, and it forms a bond with this hydrogen and a bond with that hydrogen. But they're covalent bonds, right? Nobody wins, they share. But the electronegativity of oxygen is greater than it is for hydrogen. So you get a pull from oxygen on electron density toward oxygen. It's not enough to make an ion, but it is enough to move the electron density toward oxygen. And that gives a slight positive distribution toward hydrogen, slight negative toward oxygen. And we designate that with this small delta, which is a Greek letter, with a positive charge. That just means it's not a complete charge. It's only a partial. Another way to represent it is on this bond, the positive is toward this end, the negative is toward that end. That's called a dipole. And we use that funny arrow to represent a dipole. Right? So that's the way the bonds are oriented, right? And this is a bent molecule. We talked about that when we did the Vsepr model and tried to determine the geometry. So when you add these together, they tend to form an overall dipole in that direction. So this is for the molecule, this is for the individual bonds. There are 2 things that need to be determined in order to find out if a molecule is polar. 1, it has to have polar bonds. If the bonds are nonpolar, you stop there. The molecule cannot be polar. But if you have polar bonds, then you have to ask the question, what's the geometry? Because if you have a molecule where the bonds are polar, but the geometry balances all the partial charges and cancels them out, then you have a nonpolar molecule, even though it's got polar bonds. For instance, about carbon dioxide. carbon, and then 2 oxygens. Let me just put them out here somewhere. Remember when we were drawing the Lewis dot structures for molecules, we say, all right, how many electrons are available in the valence shell? This carbon has 6, this oxygen has 6, this one has 6, this one has 4, right? Because carbon comes from this group, the 4th group, it has 4 valence electrons, oxygen has 6. So we have a total of 16 in the valence shell. So then we start positioning them, right? First, you put a single bond here and here. So that's 2, 4, minus 4 equals 12. Then you take those 12 electrons and you position them working from outside in, making an octet as you go. So this one we can put 2, 4, 6, 2, 4, 6. That's 12. So now all the electrons that we started with are back in the molecule. The problem is carbon doesn't have an octet. Oxygens have an octet. Carbon does not. So how do we form an octet with carbon without destroying the octet for the oxygens? You form another bond. So you take this pair and put it over here. Take this pair and put it over here. Now you have so now that we have this dot structure, we go to our Vsepr model and say, all right, what does it mean when the central atom is attacked, when it has 2 groups attached to it? So 2 groups means a linear molecule. 2 groups equals linear. So that molecule is written correctly, it's linear. Now, what about the dipoles? Well, oxygen is a strong attractor for electrons. So you get a dipole this way and that way, and they're equal. So that means they cancel each other out, and the molecule is nonpolar. So there's a case where you have polar bonds, but a nonpolar molecule because of the geometry. Let's see. How about all right, let's go back to writing formulas. And let's use polyatomics. I can't share the periodic table and the polyatomic list. So if you've got the polyatomic list handy, pull it out. And let's say we want to write ammonium phosphate. You know these are polyatomics because there's no element in the chart that's ammonia, whatever. Right? There's no element like that. Similarly, with phosphate, if it was just phosphorus as the element, it'd be phosphide. Phosphate means it's a polyatomic. So you look them up in your chart, your table. What is ammonium? Ammonium is NH4, 1 plus charge, always. The charges on the polyatomic ions are fixed. They never change. The phosphate is PO4 with 3 minus charge. Okay? So we have to balance the charge, but with polyatomics, you cannot break up the formula. It has to be intact because that charge is not assigned to any of the individual elements. It's assigned to the entire unit. So if you need more than one of them, you have to use a parenthesis. So we need 3 pluses to balance those 3 minuses. And that's your formula. You don't have to write the charge in it when you do that. So it's NH4, parentheses 3, PO4. That's ammonium phosphate. Let's take another one. How about this one? If I tell you to write iron 3 cyanide, first of all, what type of compound is this? What I mean by that is it type 1, type 2, or type 3 for naming purposes, right? Nomenclature. This is a type 2. It has a metal and a polyatomic, but the metal does not have a fixed charge. In other words, it could be a different charge in a different compound. So we have to say what the charge is. And that's characteristic of all the, well, most all of the transition elements. And some of all these transition elements in here, right? And some of these down here have multiple charge possibilities. In the transition metals, zinc is always 2+, cadmium is always 2+, silver is always 1+. So you can technically form compounds with these metals as a type 1 compound where you don't have to say the charge. But I've told my classes that you can put that in there if you want, simply because it's simpler to say that. But when you get out in the real world, zinc, silver, cadmium, they'll never say what the charge is, because it's always either a 1+ or a 2+. Okay, so now we know this. What do we know about iron? Iron is a 3+ charge. Right? Cyanide. Cyanide's not an element. Cyanide is a polyatomic. So you look in your polyatomic table for cyanide, and you find that it's this one, like that. So now you need 3 minuses to balance that 3+. You write it like that. Okay. Now, if we were counting up how many atoms are in that formula unit, well, there's 1 plus 3 is 4 plus 3 is 7. Right. Remember, when you're counting up, this subscript applies to everything inside the parentheses. Now, suppose we need to know the molar mass of that compound. Say we've got 100 grams of it. We want to convert it to moles, right? So if we want to convert that to moles, we say, well, for argument's sake, we have 100 grams. We want to convert that to moles. You need a conversion factor that will cancel grams and leave you with moles. And whenever you see grams and moles as a quotient, right, a divider, a division, that's molar mass. So how do you determine molar mass of this compound? You add up the molar mass of each element times how many there are. So we have 1 iron, right? So 1 iron would be, let's see, it's kind of hard to see, 55.85. Right. So let me write those out here. So it's 55.85 for iron, and 3 carbons. So you have 3 times 12.01, and 3 nitrogens, 14.01. So now we can multiply these out and add them all together. All right, that's the carbons, and then the nitrogens. So I get 133.91. grams per mole. So you put that in here. And remember, that's a conversion factor. And what do all conversion factors have in common? They're all equal to 1. They start with an equivalence. So this mole is equal to that grams. Okay? So that's why you can form this ratio and multiply it times this, because anything times 1 is not changed. We're just changing the units. The size of that doesn't change. We're expressing it in different units, which will be in moles. So 100 divided by that value is 0.7, let's see, 3 significant figures, 0.747. Okay? So you can do that with any compound, but you have to write the compound correctly. If the word problem gives you the name of the compound, you have to write it correctly. Otherwise, you're dead in the water. You cannot proceed. That's why I hammered nomenclature so heavily. If you don't know how to write compounds, you might as well withdraw from the course. Because from here on out, you won't be able to proceed. All right. And I'll just repeat, during exams, you can have a periodic table. You can have the table of polyatomic ions. You can even have the helpful hints for balancing equations. I think those 3 are in useful information for exam 2. All right. So let me see. I kind of deviated a little bit. So let me get back on track here. Okay, when we talked about covalent bonding, where you shared electrons, the examples that I'm showing so far have been one electron comes from one atom, the other electron comes from the other atom. But there's a special kind of covalent bond that's formed between one reactant and another, where both bonding electrons come from one side. A good example, if we draw the structure of dinitrogen, we will get that like that. Okay. If we want to add an oxygen to that molecule, it's already got its octet, right? 2, 4, 6, 8. 2, 4, 6, 8. Those nitrogens are perfectly happy the way they are. But if we force an oxygen on them, we force them to react in such a way as to add an oxygen to that molecule, how is it going to happen? Well, they're already happy. An oxygen comes in, like that. Right? So, how is it going to form a bond in here? Well, what it does is it takes these two electrons, makes the bond, and these two are lone pairs. So we would do this, and then you would have a bond here with that oxygen, and all of its electrons, all 6 of them, are now non-bonding lone pairs. Whereas this pair forms the bond. Now we still have 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Right, so everybody's got an octet. The thing about it is, the bonding pair of electrons came from one side. Okay, now the thing about this is called coordinate covalent bonds. The thing about the coordinate covalent bonding is, once the bond is formed, it looks like any other bond. Right? You can't tell from looking at that where the electrons came from. Right? We have to deduce that from the reactivity and the bonding process between these and here. That's the only way to know that it's a coordinate. Otherwise, if you're just given this, you can't tell. There's no way to prove it. So how do you know it's coordinate? Well, you look at the reactants, and if one of the reactants already has its octets, then it's a pretty good bet that when it bonds with something else, there's going to be a coordinate covalent bond forced upon it. All right. Let's see. Okay, so now let's extend our conversation about the different types of bonds. Okay. So we have, and this is in terms of electronegativity, right? So if we have, let's see, let me use an arrow. The trend in the periodic table for electronegativity is increases from lower left to upper right. Okay, so you should get, as you go up in a group, the electronegativity increases. As you go from left to right in a period, the electronegativity increases. So that's why lower left, upper right is the trend for increasing electronegativity. In fact, fluorine is the most electronegative element in the periodic table at 4.0. And the least electronegative is cesium at, scratching my head, maybe 0.3, something like that. So how do you know, how can we predict whether a bond is ionic or covalent, or if it's covalent, is it polar or nonpolar? Right? Well, there's kind of a rule of thumb or a table. Actually, it's in your textbook. And if we say you take the difference between electronegativities and the elements to find out the polarity of the bond. So if you have a bond that's between 0 and 0.4, difference in electronegativity. I use a delta there for difference. That's what delta means. Difference in electronegativity is 0 to 0.4. Then this is not only covalent, but it's non-polar covalent. And now we're just talking about the bond, not the overall molecule, just the bond. If you get a difference between 0.4 and 1.5, Now, and these trends are experimentally determined. In other words, we measure the polarity of these bonds and subtract the electronegativities of the elements involved in the bonds, and then we derive these trends from that. Right? So it's not, I'm not just pulling this out of thin air. Between here and here, we have a polar covalent bond. Okay? If we go from 1.5 to 2.0, we have a decision to make. If it's between a metal and a non-metal, then you have an ionic bond. If it's between a non-metal and a non-metal, it's polar covalent. Okay? That's just the nature of the beast. If we go greater than 2, right, the difference is greater than 2, then it's automatically ionic. And in order to be ionic, it's going to be a metal and a non-metal. That's the only option you have. You don't have this much difference in electronegativity between any of the non-metal atoms. Okay? So that's how we characterize the bonds. And then, of course, if you want to know for the whole molecule, you have to do the geometry. Let's see. So while we're on this topic, before I leave this topic, let's review the Vsepr model. Okay. If we have, and remember when I say the Vsepr means valence shell electron pair repulsion. So what we try to do is when we're looking at the geometry of a compound, a molecule, you look at how many electron groups surround the central atom, and then you position them for the least repulsive effects. That is, put them as far from each other as possible. Now, I take issue here. It's not just pairs, it's groups. Right? So VSEGR would be my abbreviation. But as long as you recognize when we say pair, groups also function. So what do we mean by that? Well, let's take an example. Be sure I got this, keep that on screen. If you have carbon tetrachloride, right? So you have carbon and you have 4 chlorines. So each chlorine has 7 valence electrons times 4 is 28. Carbon has 4. So we have a total of 32 electrons. So carbon is your central atom, and then you form 4 bonds to the chlorines. 2, 4, 6, 8. So that's 24 electrons. Now you position the 24 electrons, working your way from the outside in, making octets. So I already know that's going to be 2, 4, 6. 6 times 4 is 24. We've used up all of our electrons. All the chlorines have an octet. Carbon has an octet. So that's the Lewis dot structure in 2 dimensions. Right? But in 3 dimensions, when you have 4 groups around that central atom, the most efficient position for those chlorines is a tetrahedron. And that's because each bond is polar. Oh, I already did that one. Each bond is polar, but you have 4 groups. So those 4 groups are most efficiently positioned in a tetrahedron. So it would be something like, right, you'd have a chlorine here, chlorine here, chlorine here. Carbon's in the middle, right? Carbon's in the middle. And then you have a chlorine at the apex. Okay, you know what a tetrahedron looks like. And that positions those bonded electrons in such a way as to minimize their repulsion. Okay, so with that in mind, when we use this Vsepr model, the first thing you have to do is find out the electronic geometry. Right? Lone pairs count also. Right? So if you have water, right? There are 2, 1, 2, but oxygen also has 2 non-bonding pairs. So for the electronic structure for water, you have 1, 2, 3, 4. That's a tetrahedron. But the tetrahedron for water will put oxygen in the middle. It'll make hydrogen here, a pair there, and then a pair at the apex. Okay, so if you visualize these 2, right, that's just for the tetrahedron. The actual bonding is between oxygen and hydrogen. So you got these 2 sticking out here, you got those 2 up there, and what that gives you is a bent molecule, the molecular geometry. So you have to do the electronic geometry first, then you cover up the lone pairs, and you say, what does that leave you with? A bent molecule. Okay. So in order to do the electronic geometry, we have to know what the numbers of groups of electrons surrounding a central atom will give us in the most efficient geometry. So if we have the number of pairs surrounding the central atom, and then the electronic geometry, it looks like this. If you only have 1 pair, like carbon monoxide, it's got to be linear. There's no other choice. You're going straight from one atom to the other, right? But if you have 2, electron pairs are actually groups. That's also linear. If you have 3, we call it trigonal planar, which means an isosceles triangle, right? In one plane. Right, so you have things out here, and the central atom in the middle. Okay, trigonal planar. If you have 4, we covered that one already. That's tetrahedron. If you have 5, it's a trigonal bipyramid. So what you would have is this trigonal in the center, and then you would have one apex, something up here, and something down there. So I give you 1, 2, 3, 4, 5, just like that. And we're not going to go any higher than 6. If you have 6 electron groups surrounding a central atom, that is an octahedron. And an octahedron has 8 sides, right? But it's easier to visualize if you look at it as a square bipyramid, right? You put a square in the middle, and then you put one up here and one down there. Okay, so that's the electronic structure. Then to determine the molecular geometry, you have to eliminate the lone pairs and see what's left over. And I don't think we went into a whole lot of depth with that. I just introduced the topics. Yeah. So for this introductory course, we're not going to hammer the geometry too much. In order to just be aware and be able to write the Lewis dot structure for your molecule, and then apply this to your electronic structure. If you want to get into more depth in the future, then you have to sign up for CH213 general chemistry. All right, so now let's go to okay, all right, before we leave this, we leave this, we do need to go molecular geometry. All right, so let me use an example. Try this one. Okay, so how would we name that? Well, we look at where they're coming from, right? Hydrogen, in this case, hydrogen would be counted as a nonmetal with another nonmetal. So we're type 3. So we just say phosphorus, trihydride. Okay. Now let's write the Lewis dot structure for that. Phosphorus is over here. And let's see, let me get my mouse back. Phosphorus is over here. So it's 3 minus. And we use this, actually, no, not the charge. Valence electrons. 5 valence electrons there. So we have 5 here. And we have 3 times 1 there. So we have a total of 8. 8 valence electrons. So we have phosphorus in the middle, and we form a bond each with hydrogens. You can do it any way you want to at this point. It doesn't matter. So 2, 4, 6. Okay. So we have 6, have 2 electrons. So we have, you can't put any more electrons on the hydrogen. So you have to put them on the phosphorus. Okay. So now we have, hydrogens have the duet rule, right? They can only have two hydrogen and helium can only have 2 electrons because they're filling the 1s orbital. That's it, they're done. So these 2 here, 2 here, 2 here, and then 2, 4, 6, 8 for the phosphorus. Okay? So, what is the electronic geometry for this one? Well, look, phosphorus is central. You have 1, 2, 3, 4 electron groups. Right? So 4 groups means tetrahedron. Okay, so we know that the electronic structure is a tetrahedron, and the most efficient way to write it is to put hydrogens here with our phosphorus in the middle, and then the lone pair is at the apex. Right? So where is phosphorus in that arrangement? It's lifted up. It's not in the plane with these hydrogens. It's lifted up into the center. So when you cover this up, what is its molecular geometry? Well, now you have a trigonal pyramid, right? A triangular based pyramid with phosphorus at the apex. So now with this one, we have a trigonal pyramid. That's the molecular geometry. Let's see. Let me try one more. Let's try this one. Boron Trihydride. So how many valence electrons in boron? See where it is on the chart, right? Yeah, this 3. Got 3 valence electrons. 1 each for hydrogen makes 3 here. So we have 6 total electrons. So we put boron, and then we put hydrogen, hydrogen, hydrogen. 2, 4, 6. That's it. We're out of electrons. So in this case, boron is less than an octet. And why can we do that? Because this is a real compound, right? We don't develop our theories and say all the compounds have to obey our theories. We find the compounds and we make the theory fit the compound. So in this case, this theory and procedure, we just have to accept the fact that boron is deficient in octet. Well, what is its structure then? Well, it has 1, 2, 3, right? 3 groups. And that equals trigonal planar. Okay? That's the electronic structure. That's also the molecular structure because we have no lone pairs. Okay? Now, there are cases where the central atom can exceed the octet. Those generally come from anything below phosphorus, sulfur, silicon on down. Because when you get down there, you're starting to have access to d orbitals. So at that point, you don't necessarily have to have an octet. Octet is for S and P. Remember, S maximum is 2, P maximum is 6. That's where you get the octet. But when you have access to Ds, you can put anything out here. Right, so you can go on up. All right. So now let's move over. We've got, what do we have till 11 o'clock. All right, so I got another 45 minutes, and I know I'm not going to finish, so I'll deal with it. And just keep talking till I finish the topics. What is Avogadro's number? Well, we know Avogadro's number is a number of things, and it's equal to 3 decimal places, right? So it was originally derived from the fact that, well, Avogadro didn't discover it. All right, it was named in his honor simply because he proposed the principle that led to the determination of this number. Right? So remember what Avogadro said. I think we've covered that topic, but he said that if you have two gases, separate gases, doesn't matter what they are, they could be helium, argon, hydrogen gas, oxygen, carbon dioxide, whatever, it doesn't matter. You have two gases, these volumes are equal, and they're at the same temperature and the same pressure. Then the other thing that has to be equal is the number of molecules in each one. They have to have the same number of particles in each one. Well, that number of particles is given a name, and if you have this many particles, we call that a mole. Okay? Now, this is not just pulled out of thin air. This number, and it goes out to many more decimal places, is experimentally determined. There are a number of different ways to do it, and over the decades, different methods have been devised for determining what that number is. But what's the value of that number? The value of that number is that if you have that many units, 1 mole of any substance, atoms, molecules, whatever, ions, then if you have a mole of those, then we know exactly what the mass is. And I draw your attention back to, excuse me, let me erase some of this stuff that's kind of getting in the way. Where's my eraser? Where's my eraser? There it is. Okay, there we go. So if you look at each one of these elements, then you see in this chart, in the upper left-hand corner of each one of these boxes, a number. That number is the molar mass of that element. And what that means is, if you have 1 mole of that element, that many atoms, it will weigh that many grams. All right. So for aluminum to 2 decimal places, it's 26.98. So what can we do with the mole? What can we do with Avogadro's number? We can determine how many atoms, how many molecules there are if you know the mass, and have the mass, and you know the molar mass. So we've already determined molar mass of some representative compounds. You just add up the individual masses of all the elements. This value here also has another meaning, which is useful in limited application. But what it means is that is the number of atomic mass units for 1 atom. Right? So let's see, let me blow this up a little bit. Yeah, it's easier to see. So let's see, for zinc. The atomic mass units for one atom of zinc is 65.38. Okay, and remember, it's a fraction because it's a weighted average. And that's because there are isotopes. There are different masses of the zinc atom out there. So this is a weighted average for zinc, that value. And it's also based upon, let's see, since I blew it up, I've got these lines that are in the way. There we go. We need a standard. Remember, the standard for atomic masses is one special isotope of carbon. Carbon 12 is exactly that many atomic mass units per atom of that isotope. So when you look at carbon, let's see, let me expand this just a little bit. Hold on, mouse. Try it again. There we go. There's your carbon, 12.0107. Now, if that's the standard, why is it a fraction 2? Because that's the standard. But in nature, you have carbon 13, you have a little bit of carbon 14, and you have some other isotopes. And that value represents the weighted average for carbon. Right? The only one that is the exact whole number is carbon 12. Okay, so what can we do with Avogadro's number? Well, you can answer questions on a test, of course. And one of those might be something like, let's see if I can find an example. Okay, so let's try this one. Let's say we have 10.4 grams of silicon. All right. And we want to know, the question is, how many atoms is that? Right? There's no conversion factor that'll get you directly from grams to atoms. So we're going to have to use a chain conversion. Right? So first we have to convert grams to moles, because the number of atoms is a counting value, and we got to go from grams to counting. And when you go from mass to counting, that means molar mass, grams and moles. So silicon is, let's see, looking on a table here, 28.09 to 2 decimal places. Right? So now we've converted grams to moles. Now we can convert to atoms. We need to cancel moles, right, there and there, and leave us with atoms. So how many atoms in 1 mole? Avogadro's number. Right? That's the thinking part. That's the hard part. The rest is number crunching. So you would just take this times that, divided by this, and get your answer. Okay? I'm not going to calculate it out because, you know, you can do that. You don't even need my help to punch numbers into a calculator. All right. Let's see. So let's go to the next level. Let's use that conversion technique in a problem of stoichiometry. Balance the equation, and then use the balanced equation to determine amount of product, for instance. If you know how much reactant's going in, then with a balanced equation, you can determine how much product will come out. So let's use this example. Say, we want to react oxygen and hydrogen sulfide. So if we say oxygen, which is a gas, and you have to write oxygen as a diatomic, remember that. What are the diatomics? Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. We're going to combine it with hydrogen sulfide. And what is it going to produce? Well, I have to tell you that. It's going to produce water and sulfur. Okay? So if we combine these in such a way, we have to balance the equation. Now remember the technique for balancing equations, set up your budget table. So you have oxygen, hydrogen, sulfur. On this side, we start off with 2 oxygens, 2 hydrogens, and 1 sulfur. On this side, we start off with 1 oxygen, 2 hydrogens, and 1 sulfur. Right? So the only one at this point that's out of balance is the oxygen. So we have 2 here, we need 2 on this side. But now we have 2 oxygens. 4 hydrogens. Right? So now we need 4 hydrogens over here. So that makes 4 hydrogens. But now we have 2 sulfurs. So we put 2 over here. That's a balanced equation. Now, what are we going to do with that information? Let's say we have 2.1 moles of oxygen. And we have all the hydrogen sulfide we need. It's excess. So the reaction is not going to stop until we run out of oxygen, right? Oxygen would be limiting. All right, so let's make some more room. That's what we're given. What's the question? Well, let's say the question is, how many grams of water will be produced? So we want to know the mass of water. How would we set that up? Okay, remember, you can't go anywhere in an equation until you have moles. We have moles already for oxygen. So we can go from here to here in moles, and then once we find out how many moles of water, convert that to grams. Okay, so let's go from here to here. We start off with 2.1 moles of oxygen. We need a conversion factor that will give us water from oxygen. Right? So what's the conversion factor? The coefficients of the balanced equation will give you the conversion factor. 2 waters, 1 oxygen. So 2 times this would be 4.2. Right? So we got rid of oxygen. Now we have moles of water. Right? Now we need to convert moles to grams. We get this out of the way, it might be confusing. So we want to end up with grams, and we're going to cancel moles right here. So what's the magic number? For water, you need the molar mass of water. 1 oxygen is 16, grams per mole. 2 hydrogens is 2.02, like 2 times 1.01. So the total is 18.02. Okay, and that will give you the mass of water. I'm going to do this calculation just because I want to know what the answer is. So 2.1 times 2 times 18.02 is 75 point, well, 2 significant figures, so we have to round it up to 2. 76 grams. Okay, I'm getting, hold on a second. There's something wrong with my problem. Oh, here's the problem. I wrote it wrong. If that's the case, I didn't pay attention to the problem. So this needs to be 3 oxygens, 2 hydrogen sulfides, and 2 waters and 2 SO2. There we go. So the procedure is the same, but the conversion factor is different. If we're going from water here, that's 2, and there's 3. So it'll be this times that divided by that. So now let's see what it is. $25. So that means it's 25 grams of water. Okay, it helps to read the whole problem. I thought that was kind of strange. Normally, I may give an unbalanced equation, but I give you reactants and products. So now it works. All right, let's see, I got another half hour before I start going overtime. So let me see how many more of these. I've checked off some ones that I want to cover. Okay. Let's say we have these compounds. That one, this one, this one. Let's see, there. Those 3 compounds. Okay. Now let's say we form those compounds from their elements. Right? It's a synthesis reaction. So we would form this one from 1 aluminum, metal, and that gas. Right. And we do the same thing for each one of these. The question is, how many electrons have to be transferred in order to for each formula unit? Now, what does that mean? That means that these are all ionic compounds. Metal, nonmetal, metal, nonmetal, metal, nonmetal. Right. So there is a complete transfer, but we just want to know how many electrons are were transferred for each of those compounds. We don't need to know the balanced equation. Right? It'll be a different story if we balance an equation. But for this one, how do we know the transfer? Well, you need to know the charge on the ions first, right? This one is always 3+. And in conjunction with aluminum, in this formula, that would have to be 3-, would it not? So if all the electrons were transferred from here to there to make this one plus and that one minus, how many is that? That's 3 electrons. How about this one? This one's 3-, this one's 1+. Looks like a hydrogen. There. So we would have to transfer 1 electron from each potassium, and they would all 3 go to nitrogen. That's also 3 electrons transferred. How about this one? Well, barium is an alkaline earth. It's right over here. Okay? That barium tends to form a 2+ charge. Chlorine forms a -1 charge. So how many electrons are transferred in the formation of this compound? Well, that barium lost 2 electrons. Where did they go? They went over here, 1 to 1 chlorine, 1 to the other one. So the transfer is 2 electrons. Okay? Simple, simple. Let's see, what else can I say about this? All right, let's say we have helium. We're going to compare helium and beryllium. Okay. And we're told, you can look it up, of course, but we're told, let me stretch this out some. There's helium. Helium is 4.00 helium, 4.00 atomic mass units for 1 atom of helium. And beryllium, we look over here, beryllium's right over here, right there. And that's rounded off to 2 decimal places is 9.01 atomic mass units. Okay, that's given. What can we say if we have a mole of each one? Right. If we have a mole of these, we have this many. If we have that many atoms, and we also have the same number of atoms here, what can we say about the number of atoms? Well, that's a trick question. The number of atoms here is equal. If you've got a mole of that one and a mole of that one, you have the same number of atoms of both. Right? That's definition. What can we say about their masses? Right? We have the same number of atoms here as here, but each one of these weighs more. Then we can say that the mass of beryllium is greater than the mass of helium. Okay, we can say that. All right, so that's the only 2 comparisons I wanted to make. Compare the numbers, compare the masses. That just means that if we have the same number of atoms, like the Avogadro's experiment or proposal, where you have two volumes with equal numbers, what if the mass of this one is also equal to the mass of that one? Right? If you have equal numbers, then each of the atoms in this one has to be the same as each of the atoms in that one. They don't have to be the same element, but their masses have to be equal. If their masses are different, say this one has a greater total mass than this one, that means that the individual atoms and or molecules in this one must weigh per unit more than each of the ones in this one. That's the only way you can have that difference. All right. So carrying on with 15 minutes left, thereabouts. Let me see. Let's try just balancing an equation. Right? We did one before. I balanced the wrong equation, right? So let's balance one that's more kosher. Let's say we have methane, right? And we're going to form propane, right? Everybody knows propane. Well, that's the formula for propane. You crank up your barbecue grill or turn on the heat in your house or your water heater. If they use propane, that's what you're burning. But this is not a combustion reaction. This is actually the formation of propane from methane as the reactant. And you're also going to have a little bit of hydrogen left over. All right. So let me leave a little bit of room over here, right, for the coefficients. In case I need to put a coefficient in there, I need a little space. All right, so let's set up our budget. Carbon, hydrogen. That's it. Those are the only two elements in there. We have 1 carbon and 4 hydrogens over here. We have 3 carbons, and 8 plus 2 is 10 hydrogens. That's where we start. So let's be sure. 4, 5, 4, 5, 3, 11, 12, 13, 13. So I've counted all of them to begin with. Now, how are we going to balance these? Well, you remember the trick or the hint. If you have an element here, don't put anything in front of that one yet. What we want to do is balance the carbons first in this case. So we need 3 over here, right? So that means 3 carbons here and 12 hydrogens, right? 3 times 4 is 12, 3 times 1 is 3. Now, what's the most efficient way to balance this one at this point? You've already got 10 hydrogens. You need 2 more. So if we put a 2 in front of that hydrogen, that'll make 4 plus 8 is 12. That way, we don't have to put a coefficient in front of this one, which would mess up everything because it would change the carbons and the hydrogens. This way, we just change the hydrogens. So what are our coefficients? Right? If you're asked for the coefficients of this reaction, 3, 1, 2. Remember, there's always a 1 there. If you've got a formula here, then it has to have at least 1 there. We don't write it, but it's there. So it'd be 3, 1, 2. It's the coefficients. Sometimes test questions say, what's the sum of the coefficients? So you say 3 plus 1 is 3 plus 3 is 6. All right. Let me see if there's anything that I haven't covered yet. All right. Let's go back to electronic configurations for a second. let's say we have this one. 1s2, 2s2, 2p6, 3s2, 3p. Oops, sorry. No, that's right. 3p6. 3p6. 4s2, 3d10, and 4p3. Okay? We don't know the element. I mean, it's not given to us. But the question is, how many valence electrons are here? So you have to go back to your definition. How do you count valence electrons? You go to the highest principal quantum number. In this case, it's 4. And you count up all the electrons that are in that level. So there are 2 here and 3 there. Right? You don't count this one. Even though it's in that order, different order, you count the highest number. So it's 2 plus 3 is 5. So you have 5 valence electrons. Okay, so where would that likely put it in our periodic table? Look here, there's 3, there's 4, there's 5. It's probably in that column somewhere. So can we determine what element it is? Well, there are a couple of ways to do it. Right? Add up all these. 2, 4, 10, 18, 20, 33. 33 electrons, which means if it's a neutral atom, there are also 33 protons. Aha. If that's the case, then 33 is, we're looking for the atomic number 33, which is arsenic, right here. Okay? What's the other way? Well, the other way is if you know the structure of the periodic table, you can tell that you've gone through period 1, all the way to period 2, all the way through period 3. Here, here. And D's have 10 electrons, right? So you've gone all the way through this period here, over to this period, and then we've gone down here to these. But how did you get there first? You had to go through 4 S's, right? Remember, 4 S's first, and then you go through the D's, 3 D's, and then you get into the 4 P's. 4 P's, 1, 2, 3. Arsenic has 3 P electrons. Okay, so we can identify the element based on this electronic structure. If it were an ion, then you'd have to know what the charge is. Okay, what if, let's try another one, using the periodic table. Okay, I keep moving my board around. Let me center it again. There we go. Let's say we have a metal and a non-metal. This metal, M, is from group 3A. Okay, and the non-metal is from group 6A. So you look at your periodic table and you say 3A, where is that? It's right here, 3A. What's the charge? The 3A's have a +3 charge. Okay. So you have this one like that. And then 6A is here in the oxygen group, the chalcogens. So it's a 2- charge. Now, what would be the correct formula for this MX? Doesn't matter what the elements are. right? We're not interested in that. We're only interested in how do you write the correct formula. Well, you need, when you have an odd and an even, plus minus or minus plus, cross multiply. Put the 2 over here and the 3 over there. So 3 times 2 minus is 6 minus. 2 times 3 plus is 6 plus. And your charges are balanced. So that would be the formula for this compound, whatever the M, whatever the X, it doesn't matter. All right. I may be able to finish this after all. Let's see. All right, what kind of, if you're given the electronegativity for carbon is 2.5. Electronegativity for carbon is 2.5, and it forms a bond with hydrogen. Right? So we have this bond. Doesn't matter what else is around it. We're just focusing on that bond. What type of bond is that? Is it nonpolar, covalent? Is it polar covalent? Is it ionic? Well, look at the difference between the two. The difference is 0.4, right? So, non-metal with a 0.4, and remember the difference up to 0.4, I believe it was. Scratching my head. 0.4. Look at my notes. Yeah, up to 0.4, that bond is non-polar. Okay. What if we had, let's see. Well, we need to know the electronegativities to do any supposition, and I don't have that chart with me. So that has to be given in the problem. All right, let's see, where was I? Before I so rudely interrupted myself. Let's balance another equation. Let's do a harder one. So let's say we have C4H10. Let's see, C4H10 plus, oh, we're going to burn it, combustion, and then it's going to produce carbon dioxide and water. There we go. So let's balance that one. Set up your budget, carbon, hydrogen, oxygen, and then we do our initial tally. 4 carbons, 10 hydrogens, 2 oxygens on that side. Let's see, that's 4, 14, 16. 16 there. Carbon on this side is 1, hydrogen is 2, oxygen is 3. 2 there and 1 there. Right? So that's 3, 4, 5, 6, 3, 3, 6. Okay, where do we start? Well, we don't want to do oxygen first. First of all, oxygen is an element on this side. It's in 2 places on this side. That would be a problem. So let's start with carbon. 4 carbons here, 4 carbons there. Now that changes the number of oxygens from 3 to 8 plus 1 is 9. Okay? Now how about hydrogens? We need 10 hydrogens, and they only occur in one place over here. So we'll say 5 makes 10 hydrogens. But it also makes 5 plus 8 is 13 oxygens. Now let's see, is that right? 4 plus 8 is 12, plus 5 is 17, plus 10 is 27. So 4, 13 is 17, 10 is 27. Okay, so I haven't missed anything. Now we've got 4, 10. We need to balance this prime number against an even number. Well, 2 is a prime number too. But it's difficult to do, right? There's no number you can multiply over here that will give you that, except a fraction. So to get 13 oxygens on this side, 13 halves, right? A half of that molecule is 1 oxygen, times 13 is 13 oxygens. But we're not done yet, right? Because we don't like to leave fractions. So how do you get rid of that fraction? You multiply the whole thing through by the denominator. Now, why can I do that? It's like any equation. If you have an equation, a mathematical equation, you can multiply both sides by the same number. And you still have the same equivalence. This is an equivalence. You've already established by balancing these atoms, you've satisfied the condition for balancing mass of reactants with mass of products, because the same number of elements on both sides of each, same number of atoms of each element on both sides. So the ratio of 1 to 13 halves to 4 to 5 is now chiseled in stone. That is the ratio of each of the reactants and products. So if you multiply it by some other number, as long as you multiply everything by the same number, you have not changed the ratio. So multiply through by 2. Now this one becomes 2. Right? This one becomes 13. This one becomes 8. And this one becomes 10. So now the whole number ratio is 2, 13, 8, and 10. All right. The only trick we didn't use here was polyatomic ions. Right? If you have polyatomic ion here and here, reactants and products, it doesn't occur anywhere else, and it's not shattered, it's not broken up in the process, you can use the polyatomic as a balancing group, and it saves a whole lot of work. All right. So let me see. I got 1 minute left, I think, or maybe my time is up. I think it ends at 10:59. Let me see just to be sure. Yep, 10:59. So let me see if there's anything else I want to cover for this review for exam 2 on chapter 4, 5, and 6. And this exam's not due until the 26th of March because we're going over spring break. So you've got time to study up for it. And you can take it as long as you have taken exam 1. Exam 2 is available to you. If you did not take exam 1, then exam 2 will not open until you have taken exam 1. Right? So I know a couple of people that haven't taken exam 1, they're going to send me emails and wonder why I can't get in exam 2. That's the reason. Okay, let's see. Isoelectronic. We didn't discuss that. What do we mean by isoelectronic? Very simply, 2 species, they can be atoms Actually, if they're iso, no, they have to be, one can be an atom, but the other one may be an ion, or you could have two ions. In order to be isoelectronic, their electronic structure must be the same. Iso means same. That's the Greek prefix for same. Isoelectronic means they have the same electronic structure. So if we were to take helium as our starting point, right? Helium, excuse me, neon 10, the electronic structure would be 1s2, 2s2, 2p6, 6, 7, 8, 9, 10. All right. What could have the same electronic structure as that? Well, let's look at fluorine. Right? It's only got 9. So it would be 1s2, 2s2, 2p5. So that's not the same. But if we allow fluorine to acquire an electron from some other metal and make it a negative charge, one charge, now that and that are isoelectronic. What if we went the other way? Let's say we went to sodium. Sodium would be 1s2, 2s2, 2p6, 3s1. That's not isoelectronic with either one of those. But sodium's a metal. It wants to go to this octet. So it would give up that electron. Now that's 0. Now it also is isoelectronic, right? And that's the way you do the series. One can be neutral. And you can start from this one as neutral and say, what other things can you do to make 2p7? Right? Then you would have to be able to justify the transfer of electrons either away from or to, added to, in order to produce the same electronic structure as your starting material. All right. So let me see. Any other topics that I want to cover? That covers it. Right. So what you want to do is view this video. Well, by now you should have already seen the whole thing. And if you have any questions about what was done here, if you're not comfortable working problems in any of these examples that were given, then you need to go back and focus on that type of problem. Go into your book. You can find problems in the chapters. You can find problems at the end of the chapter. And I've given you numbers, those that I'd like you to look at, but you can do any of them you want. And work as many of them as you can. Right? 2 things that are your best friends in chemistry. Curiosity. You want to know why. You want to know more. You don't just sit on a log, work a problem, pass a test with a C- and happy with yourself. If you really want to know chemistry, you got to stay curious. You want to know more and why. And the other best friend is boredom. When you work problems, if you work the same problem over and over and over again, you'll eventually get bored with it. That's a good sign. If you're bored working a problem, and you get the right answer each time, of course, if you're bored, then it's up here. You got it. All right. So that's enough of my pep talk. I'm going to be grading all your work. I have to turn in grades on Monday, the 15th. So I've got to get all of your well, any exams that you haven't done, there's only been one exam. So if you haven't done exam 1, you better get it in before Monday, because if you don't, it goes in as a 0. Labs, if you haven't turned in your labs, turn those in. I'll get them graded by Monday so that you'll have access to those grades. If you haven't turned in a lab and it's due, look at the syllabus, the schedule. It'll tell you which ones are due. If you don't have a grade in your My Grades, go into Blackboard and look at your My Grades. If you don't have a grade, they're posted in a lab that you have submitted. Then those will be graded by Monday and incorporated. But if you haven't submitted one that's due, then I will stick a 0 in that slot just as a reminder to you. And that 0 will go into your average, right? And that's not good. I mean, getting a 0 because you didn't do the work is just ludicrous. If you get a grade, a downgrade from work that you've turned in, at least you've got a grade that's greater than 0. So I never understood that, why students wouldn't turn in their work, either as an instructor or as a fellow student. I say, those students that are in my class with me and I'm taking this class, you didn't turn in your work. I mean, I don't say this about many things or many people, but that is just plain stupid. Okay, so that's it for the review for chapter 4, 5, and 6, exam 2, that you can do between now and the next time we meet, the week after spring break. And again, if you haven't done exam 1, you will not have access to exam 2. So don't even ask. You either work exam 2 or you just miss both of them. Exam 1. You either do exam 1 and then you have access to exam 2. If you don't do exam 1, then you'll get 0s on both of them. All right, I'm gonna stop this share. Let's see, there, stop the share. And since there's nobody left in the class, I'll call it a day. End the meeting, and the recording will be up in a day or 2.